Hi everyone, welcome to this session. So today we will be solving this very interesting interview question. Okay, basically this is a MOSFET based circuit, and this is pretty simple circuit, right? We can see that basically here we have two MOSFET, M2 and M1, and they are connected in this fashion. Okay, and we have a V bias there. Okay, so basically the overall circuit is properly biased at saturation. Okay, first question is calculate the bias current ID1 and ID2 with proper direction. Okay, so what will be the answer? So we can see that the current will flow in this direction, right? In this direction, ID1, right? And what will be the direction of ID2? So for bias condition, we know that the for a PMOS, so this is a PMOS, right? For PMOS, the bias current is flows from source to drain. So this will be the and the direction of the ID2 will be nothing but this way. Okay, so this is the ID2. So now, and this is a series path, right? This and this comes in series, right? So all two of these current will be same. So ID1 will be ID2, and if we write the equation, this will be nothing but what it would be. So we know that this will be nothing but half into mu n cox wl of, let's say, n mos, okay, into vgs minus vtn whole square, right? So here vgs is nothing but v bias itself. Okay, basically this is a large signal. Okay, the biasing voltage. Okay, so this will be nothing but v bias minus VTN. Okay, so threshold voltage of this NMOS. Okay, and whole square. So this is the current equation, and this current is equal to the this current, right? The current flowing through PMOS, right? In this direction, right? So this is pretty easy and pretty simple. Now the question is, if we add a del V change there here, okay, then what will be the small signal currents for these two MOSFETs? Okay, so let me draw the picture again. Okay, so this was our picture, right? So for small signal, this will be AC grounded, right? The VDD. So this is our M2, and this will be our ground as well, and this is M1. And here we have just apply a small signal del V, right? Because it was previously biased, right, at saturation. Okay. So now, so what we can say? What will be the current through this MOSFET? This one small signal current. So this will be nothing but GMVGS, right? GMVGS of 1, and this is nothing but the GM of this MOSFET. This is GM1 times the del V, right? This is the current flowing through in this direction, right? From drain to source of this M1, right? So we know that the small signal model of PMOS and NMOS is same, right? So, and we are neglecting here the R out. Okay, so basically here the channel length is neglected, so the lambda value is 0. So we are not considering about the output impedance here. Okay, for our easy calculations. Okay, now, and so this is the case, right? So this small signal current is nothing but gm1 times vgs1, and this gm1 times, let's say, del v, right? So this is the case. So here we have applied del v. This is for gm1, right? Like this part. Now what about this? We know that for small signal, the model for small, like the for PMOS and NMOS, the small signal model is same, right? So the model is nothing but this. So the current is always, the small signal current I is always flows from drain to source, right? We know that, and this is nothing but GM times delta, like small signal VGS, right? We know that. But in this case, so we can see that the a small signal current I1 is flowing in this way, right? So if the case, if the like the KCL has to be satisfied every time, right? So a small signal current must flow through in this way, right? So that the KCL will be maintained, right? So basically here is a black box, and here a small signal current is flowing, right? I1. So now this current has to comes from this black box, right? So this black box is nothing but our this PMOS, right? But we can see that this is the source and this is the drain. But we know that the small signal current is always flows from drain to source. But here these things is like the this is opposite, right? Because this is the source and this is the drain of this PMOS, but the current has to flow in this way, like from source to drain. But like it is contradict, right? For a PMOS small signal model. So how to get how to solve this, like what we can comment. So is this wrong? Actually this is not wrong. Okay, why not wrong, I am telling. So okay, let me draw the picture again. So this was our PMOS and this was our NMOS, and a small signal current is flowing through this path due to this del V change in gate, okay, of this M1 now, right? And this small amount of current has to flow through this way to satisfy the KCL. But for PMOS we know that the small signal current is also flows from drain to source in this way, right? But here we can see that the current has to flow from source to drain. Why? Well, like how it is happening? Because this is the ground part, right? So current can flow in this way if this voltage is lower than this ground, right? So this has to be a negative voltage, and because actually there is a negative voltage present there. Why? Because from this to this, from here to there is a 180-degree phase shift, right? So if there is a delta V change, there would be a minus del V change with a gain of this circuit, right? Like the voltage at this node will be nothing but like del V times minus of the gain, right? At this node, right? So this node is low, this node is like, okay, let me. So this node is at higher potential that node, right? So basically this potential, let's say Vx, will be nothing but minus of gm1 times what will be the gain. So gain will be nothing but this, the impedance at this node. So this will be nothing but 1 over gm2 times del V, right? So basically in this case, in this node there present a negative voltage. So this potential is positive and this potential is more positive than this potential. So a small signal current can flow through source to drain. Okay, so this is how we can interpret this small circuit. Okay, so this is the thing. So actually we are finding that if we are okay, let me draw the picture again. So if we are changing say small amount at this node at this voltage, so small amount of current will flow in this way, and same current has to flow in this way as well, right? But this may look contradict these conditions, because we know that for small signal the current the current of, like the small signal current of a PMOS and NMOS is always flows through from drain to source. But in this case, as there is a present a 180-degree phase shift, so this potential becomes negative than this zero potential. Okay, so that a small signal current has to flow in this way. Okay, so this is how the small signal current is flow. So the id2 will be equal to, and the id2 will be nothing but the direction will be in this way. Okay, so the overall current is flowing in this path. So id1, small signal id1 will be equal to id2 will be nothing but gm1 times del v, right? Del v, like this del v, right? So this will be plus case. Okay, so all of this current is flowing in this direction. So for m1 the current is flowing from drain to source, and for m2 the current is, small signal current is flowing from source to drain. Okay, for small signal. And for bias condition we all know, for the for PMOS current is always flows from source to drain, so there is no contradiction. And for NMOS, the bias current is flows always from drain to source, so there is no contradiction was there. Okay, so this is the thing. Okay, and the gain of the circuit is nothing but, so this is a small voltage, right? So we can find the small signal gain. So this will, and if we can take out from there, and the input is del v, so V out over del V is nothing but minus GM1 times 1 by GM2, right? And we are neglecting channel length modulation. Okay, so this is the gain of the circuit. So actually the trick was that to mention that this potential becomes negative, small signal, okay, so that the small signal current can flow from source to drain for a PMOS. Okay, so this is the thing. Thank you everyone. I think you get a little bit of insight of this circuit, of this small circuit. Okay, thank you, and please give your valuable feedback. Thank you. So the direction of the current is important, like how it is coming. Okay, so this is the important thing. Thank you.